Today, our mission for you, the listener, is to completely shatter your perception of the ground beneath your feet. We are taking a deep dive into this foundational, yet I'd say fundamentally misunderstood concept of soil health.
Right.
And we're drawing from a really comprehensive Wikipedia analysis on the topic because, for most of our lives, we treat the ground as this, inert, passive sponge.
Yeah, just dirt.
Right, just dirt. It is just structure, like concrete but softer, I guess. A tree grows in it, a house is built on top of it, a farmer drops a seed into it. We just assume his only real job is to hold things up and maybe absorb a little water when it rains.
Which is, it's a perspective that reduces one of the most dynamic environments on Earth to mere scenery.
Yeah.
When you actually look at the source material and the science that has evolved around this, you realize that referring to soil as just dirt, or like you said, an inert sponge, it completely misses the reality.
The actual biology of it.
Exactly. It misses the biological infrastructure that dictates literally everything, from global food security to environmental stability.
Okay, let's unpack this. Because to understand what soil actually is, we first have to look at how our vocabulary around it has radically changed. Because, words matter.
Oh, absolutely.
And in the scientific community, a recent shift in terminology has kind of completely flipped the script. It seems that for decades, the agricultural and scientific communities, they didn't even use the word health when talking about the ground.
No, they didn't.
They used the phrase soil quality.
Right. The term soil quality really dominated the established scientific community until, very recently. And to understand why that matters so much, we have to look at the philosophy embedded in that specific word.
The word quality.
Yes, quality. Because the word quality implies a utilitarian functional class.
Like grading something.
Exactly. It evaluates the Earth based entirely on a specific, isolated human purpose. So when scientists or agronomists or engineers evaluated soil under this older paradigm, they were asking highly transactional questions.
Like what?
Like, is this dirt good for a roadbed? Or, is this quality of soil optimal for planting a specific strain of maize?
Huh. It sounds like evaluating a piece of lumber.
That's a great way to put it, yeah.
Like you look at a plank of wood and ask, is this good quality oak for a dining table or is it just scrap wood? You aren't really thinking about the forest it came from.
No, not at all.
Or just grading its utility for a specific manufacturing task.
That captures the mindset perfectly. It views the soil as this static, isolated resource, just a material to be graded and utilized. But the transition that has occurred, the shift to using the phrase soil health, it represents a massive departure from that manufacturing mindset.
Because health implies life.
Right. Health shifts the perception toward an integrative, holistic, and systematic view. It basically frames the soil's ability to function as a self-sustaining environment.
Wow.
So the focus moves away from, what the soil can do for a specific crop right this second, and instead looks at the intrinsic well-being of the entire underground ecosystem.
Okay, I have to play devil's advocate here for a second because I know you, the listener, might be thinking the exact same thing right now.
Go for it.
I look at corporate rebranding all the time, right? A company might rename their janitors to sanitation engineers.
Right.
Or their cashiers to guest experience associates, just to sound better on paper. But the actual day-to-day job hasn't changed a bit. So is this shift from quality to health just semantic rebranding? Does changing the word actually change the hard science of what researchers are doing in the dirt?
It absolutely changes the science because the terminology actually dictates the methodology. Yeah. Using the word health actively reject the dominant philosophy of modern intensive farming. Historically, intensive farming views the soil as an inert, lifeless, growing medium, a blank slate, essentially.
Just a vessel to hold the roots.
Exactly. The assumption was always that the soil itself didn't provide much beyond a physical anchor. It had to pump in chemical inputs to get a crop output.
Right.
By shifting to soil health, the scientific community is acknowledging that the soil is not a machine you can just pour fuel into. It's a living, dynamic, and ever so subtly changing whole environment. It has its own biological limits and requirements.
So it's the difference between being a mechanic fixing a car, where you just, swap out a broken part or top off the oil.
Yes.
And being a doctor treating a patient, where you actually have to consider how the cardiovascular system is affecting the nervous system.
That biological analogy is exactly how the discipline operates today. And, this philosophical shift didn't just happen overnight.
It didn't.
No, the source material actually traces this back to the organic and biological farming movements in Europe, well before the concept of soil quality was even formally applied as a discipline, which was around 1990.
Oh, wow. Okay.
There's a pivotal moment highlighted in the text from 1978. A Swiss soil biologist named Dr. Otto Bess, he wrote an essay titled The Health of Soil and Plants.
1978. So this conversation has been quietly brewing in the background for decades, while the mainstream agriculture industry was just going all in on industrial, chemical-heavy farming.
Yes. Dr. Bess was incredibly prescient. His 1978 essay largely defined the boundaries of the field as we understand it today.
What did he argue?
He basically articulated that you cannot separate the vitality of the plant from the vitality of the ground it grows in. They are part of one continuous living system. You cannot have a healthy crop emerging from sick soil, no matter how many synthetic vitamins you inject into the system.
Man, let's follow the logical conclusion of that, because the implications are huge.
They really are.
If we start viewing the soil as a living entity rather than a resource to be mined, it completely rewrites our fundamental human responsibility toward the environment. Think about coal mining, for instance.
Right.
When you mine coal, you are extracting a finite, dead resource until it's just gone. You leave a hole in the ground, you pack up your machinery, and you move on. Your only relationship to that land is extraction.
Right.
But if soil is alive, you can't just mine it. If you treat a living system like a coal mine, you kill it.
The transition from extraction to custody is the core of this paradigm shift. If the soil is alive, you have a duty of care. You have a responsibility to maintain its health, kind of similar to how a rancher must maintain the health of a herd of cattle.
Wow, yeah.
It changes agriculture from an extractive industry into a custodial one. The farmer or the land manager is no longer just a producer of crops. They are a steward of an ecosystem. This requires a much more complex, observant relationship with the land.
And it changes how we view real estate and land ownership too, doesn't it? When you buy a plot of land to build a house or start a farm, you aren't just buying a patch of dirt. You are taking custody of a living, breathing system. But, if we are going to commit to calling the soil alive, if we are going to say this isn't just poetry, but actual hard science, then we need to talk about the life forms that make it up.
We do.
Which brings us back to that African elephant I mentioned at the top of the show. The sheer scale of soil biology in the source material is mind-bending.
The quantitative data on soil biomass completely disrupts the way we visualize the ground. It really forces you to realize how crowded the subterranean world actually is.
Well, here's where it gets really interesting, because the numbers are almost too big for the human brain to visualize properly. According to the text, in just one single hectare of temperate grassland soil, which is roughly the size of a standard sports field or a rugby pitch, there is a documented 1 to 2 metric tons of bacterial biomass.
Yeah.
And 2 to 5 metric tons of fungal biomass.
When you combine those figures, you are looking at up to 7 metric tons of microscopic life in a relatively small plot of land.
For you listening, a metric ton is 1,000 kilograms, or roughly 2,200 pounds. So 7 metric tons is over 15,000 pounds of living organisms.
It's massive.
That is the weight of a massive adult African elephant. Imagine an elephant standing in the middle of a grassy field. Now, imagine taking the mass of that elephant, breaking it down into microscopic, invisible bacteria and fungi, and spreading it out just beneath the surface of the grass.
Right.
That elephant is down there. It is just invisible to the naked eye, silently going about its business.
And its business is what keeps the planet functioning. This massive amount of life isn't just a subterranean zoo. It is a highly functional, critical infrastructure. The source material actually notes that microbiologists now believe 80% of soil nutrient functions are essentially controlled by these microbes.
Wait, 80%?
80%.
I always assumed nutrients were just in the dirt, like salt dissolved in water. The
Right.
plant roots just suck it up. How are the microbes controlling 80% of that process?
The assumption that nutrients are freely available is a really common misconception. In reality, the vast majority of nutrients in the soil, like phosphorus, nitrogen, and complex carbons, they're locked away.
Locked away how?
They are bound up in solid organic matter, like dead leaves and roots, or they are chemically locked inside the mineral structure of rocks and sand. A plant root cannot simply absorb a solid piece of a dead leaf, nor can it extract phosphorus directly out of a solid rock.
So the nutrients are technically there, but they are completely inaccessible, like being locked inside a grocery store without the ability to open any of the cans on the shelves.
That is an excellent way to conceptualize it. The microbes are the can openers. The bacteria and fungi physically and chemically break down those complex materials. Fungal hyphae, which are incredibly fine, microscopic threads, they can actually excrete acids that dissolve microscopic amounts of rock to free up the phosphorus inside.
That's incredible.
And bacteria consume decaying organic matter and process it through their own biology, excreting nutrients in a water-soluble form that the plant roots can finally absorb.
So they are essentially the digestive system of the earth.
Yes.
We know that humans need a gut biome, right? Billions of bacteria in our stomachs and intestines to break down the food we eat so our bodies can absorb the nutrients. Without our gut bacteria, we would starve, even if we ate 3 meals a day.
Exactly.
The plants are basically outsourcing their digestion to the soil.
That is the exact biological mechanism at play. Without this microbial workforce, the nutrients remain locked away. This is why the text makes a vital connection. It turns out that soils, which are highly fertile from the point of view of crop productivity, are also the most lively from a biological point of view.
Makes sense.
You just cannot have sustained high-level agricultural productivity without a robust microbial workforce doing the heavy lifting underground.
Right. If you kill the African elephant of microbes beneath the grass, the plants starve no matter what is technically present in the dirt.
Precisely.
But this brings up a really important nuance from the source text, especially for anyone involved in agriculture who might be listening. Usually in these conversations about soil ecology, synthetic or inorganic fertilizers are painted as the absolute villain.
Oh yeah, constantly.
The common narrative is that pouring chemical fertilizers onto a field is like pouring acid onto that microbial metropolis, instantly killing the soil biome.
The text explicitly addresses that narrative to ensure a balanced, scientifically accurate view. It states that inorganic fertilizers do not necessarily damage soil health.
That seems completely counterintuitive to me. I mean, I have a personal anecdote about this.
Oh, let's hear it.
A few years ago, I had a dying houseplant. I figured it needed food, so I took a bottle of liquid synthetic fertilizer and just dumped a massive amount into the pot.
Oh, no.
Yeah, I thought more food meant more growth. Instead, the plant turned brown and died in 3 days. I basically gave it chemical burn. So how can the source materials say these chemicals don't damage the living system?
Well, your houseplant anecdote highlights the exact mechanism the text warns about, which is dosage and excess.
Excess.
Right. The key phrase in the source material is, if they are not used in excess. The problem with inorganic fertilizers is not that they are inherently evil or instantly toxic. The problem is how they are managed within a complex system. If managed carefully, the text notes that inorganic fertilizers can actually bring about a general improvement in overall plant growth, which indirectly benefits the microbes.
Okay, walk me through the mechanics of that. If I use a small calculated amount of synthetic nitrogen fertilizer, I am feeding the plant directly, bypassing the microbes, right?
Correct.
The plant grows bigger. How does that actually help the microbes?
Think about what happens when a plant grows larger and more robust. It produces a larger root mass, more leaves, and thicker stems. A larger plant is also conducting more photosynthesis, pulling more carbon dioxide out of the atmosphere.
And plants push some of that carbon down into their roots, right?
They do. They exude carbon compounds directly into the soil to attract microbes. Furthermore, when that larger plant eventually dies, or when it sheds its leaves and roots over the course of a season, it contributes significantly more carbon-containing residues back into the soil than a smaller plant would have.
So a bigger plant creates a massive buffet of organic matter for the microbes later on.
It creates a beautiful biological feedback loop. You are using a synthetic input to kickstart a biological output. The fertilizer boosts the plant captures more carbon, and then pumps that carbon into the soil as organic residue.
Which feeds our invisible elephant.
Exactly, the bacterial and fungal biomass. So in a well-managed system, inorganic fertilizers can be a calculated tool to indirectly support the soil biota.
But the tipping point is the excess.
Yes. When you dump half a bottle of fertilizer into a houseplant, or when a farmer over-applies nitrogen to a field, the system cannot process that sudden chemical spike. It changes the pH of the soil, it disrupts the osmotic balance, which is the chemical burn you saw, where the salts in the fertilizer actually suck water out of the plant roots and the microbes, and it leads to systemic failures. The nuance here is critical. The science isn't engaging in an organic, good, chemical bad shouting match. It is evaluating the mechanics of a complex system.
Which brings up a massive practical issue. If this subterranean world is a complex, living organism with digestion, infrastructure, and a delicate chemical balance, how do we actually know how it is doing?
Measuring it is the real challenge.
Yeah, because if I go to my doctor for a physical, they take my blood pressure, they listen to my heart, they draw blood. How does a soil scientist actually diagnose whether the dirt is sick or healthy?
The scientific community has grappled with this exact challenge, and to solve it, they built a comprehensive framework that is actually heavily reliant on the human health analogy. Diagnosing soil health requires looking at multiple interconnected vital signs simultaneously.
Okay, let's run the diagnostic. What are we looking for when we give the dirt a checkup?
According to the text, a healthy soil is categorized by several core traits. First, it must be in a state of composite well-being. This is crucial.
Composite well-being.
Yes. You cannot just test its chemistry or just look at its physical structure or just measure its biology. You have to look at the intersection of all three biological, chemical, and physical properties working in tandem.
So if we continue the human analogy, the physical structure of the soil is like the skeletal system, the bones holding everything up. The chemistry is like the blood transporting nutrients. And the biology, the microbes, are like the internal organs doing the actual processing.
Exactly.
A patient isn't healthy if they have great bones, but failing organs.
That analogy maps perfectly onto the framework. The second trait is that the soil must not be diseased or infirmed. In agricultural and ecological terms, that means the soil is not degraded, it is not actively degrading, and it is not causing negative off-site impacts.
So if I have a contagious virus and I am coughing on everyone around me, I'm not healthy, even if I feel okay in the moment. So if a patch of soil is bleeding toxic chemical runoff into a nearby river and killing the fish, the soil is diseased.
Precisely.
Oh.
Third, all of its qualities must function cooperatively, so that the soil reaches its full potential and actively resists degradation. It needs resilience, effectively an immune system, to bounce back from stress like a drought or a heavy storm.
Makes total sense.
And finally, it must provide a full range of functions, specifically nutrient, carbon, and water cycling, and do so in a way that maintains this capacity into the future.
Here is where the source material highlights a really fascinating conflict. Defining health conceptually is easy, but applying it in the real world is messy. Because when you say the soil needs to reach its full potential, whose potential are we talking about?
Right, exactly.
The text points out that a soil can be perfectly healthy in terms of ecosystem functioning, but completely fail to serve crop production or human nutrition directly.
This is where the discipline of soil health becomes highly context-dependent and sometimes quite controversial.
Wow.
The benchmarks for health change depending on geographic circumstances, climate, and the natural inherited qualities of the soil. But the biggest variable is human aspiration. There is a deep inherent tension between an ecological landscape assessment and agronomic objectives.
If I am an ecologist assessing land, my benchmark for healthy soil might be a dense, tangled, wild forest floor, right?
Yeah.
It has massive biodiversity, it cycles carbon flawlessly, and it absorbs every drop of rain. It is the pinnacle of ecological health.
Yes.
But if I'm a farmer trying to feed a city of 1 million people, I cannot grow 1,000 acres of wheat in a tangled wild forest.
The agronomic objective requires clearing that land, manipulating the environment, and cultivating a single crop. The farmer needs the soil to support a very specific, intensive human goal. Therefore, alternative users of the term soil health place differing priorities upon the multiple functions of a soil.
Got it.
A soil that is vibrantly healthy for a wild forest ecosystem might be totally unproductive for a farmer trying to grow maize. Conversely, a soil that has been perfectly calibrated chemically to pump out maximum maize yields might be ecologically sterile in terms of broader biological diversity.
It is like evaluating the health of a human based on whether they are a marathon runner or a competitive powerlifter.
That's a great comparison.
A marathon runner is extremely healthy, with incredible cardiovascular endurance. But if you ask them to deadlift 500 pounds, they will fail instantly. Are they unhealthy? No, they just aren't optimized for that specific agronomic task, so to speak. The powerlifter can lift the weight but might fail a 10-mile run. We are asking the soil to perform incredibly specific tasks.
To bridge this conceptual gap between the ecologist and the farmer, the text outlines some generic, universally agreed upon aspects that define a healthy soil, regardless of whether it is supporting a wild prairie or a commercial wheat field. These are the baseline vital signs.
Let's go through those baseline vital signs. What makes the cut universally?
First, productive options are broad. This means the soil isn't so severely degraded that it can only support one tough, invasive weed. It has the foundational capacity to support a variety of plant life, even if a farmer chooses to only plant one.
Okay, that makes sense.
Second, life diversity is broad. Our microbial elephant shouldn't just be one species of bacteria. It needs a complex web of different fungi, bacteria, protozoa, and nematodes. Third, absorbency, storing, recycling, and processing are high in relation to the limits set by the local climate.
Basically, when a heavy rainstorm hits, the soil should act like a deep sponge, pulling the water down into the aquifers, rather than acting like a concrete driveway where the water just pools on top and runs off.
Which leads directly to the next universal benchmark. Water runoff quality must be of a high standard. There should be very little leakage of nutrients from the ecosystem. A healthy soil ecosystem holds onto its nutrients tightly within that microbial biomass.
Now, here is a concept from the text that I really need you to explain mechanically because it sounds like quantum physics invading my garden.
Oh, I know what you're going to ask.
The text says, a healthy soil has low entropy. I barely passed high school physics, but I remember entropy being the measure of chaos and disorder in the universe, things falling apart. How does the concept of entropy apply to dirt?
The application of thermodynamics to soil health is brilliant because it perfectly describes the physical structure of the Earth. In physics, a system with high entropy is disorganized, breaking down, losing energy, and becoming chaotic.
Right.
A system with low entropy is highly organized, structured, and efficiently storing energy.
Walk me through the mechanics of low entropy in the ground. What is physically holding the organization together?
It comes down to biological glues and physical architecture. In healthy, low-entropy soil, the fungal hyphae we talked about, they weave through the dirt particles like a microscopic fishing net, pulling them together into clumps called aggregates.
Okay, fungal nets.
And then bacteria excretes a sticky substance called glomalin that literally glues these aggregates together.
Yeah.
Because of this architecture, the soil is full of structured pores and channels. Energy from the sun is captured by plants, turned into carbon, and neatly layered into this structure. It is highly organized. That is low entropy.
So the microbes are acting like construction workers, building a high-rise apartment building out of dirt particles, complete with hallways for water to flow through and rooms to store carbon.
Yes. Now, imagine a field that has been aggressively overplowed for decades. The mechanical blades have sliced through the fungal nets, the biological glues have degraded because the microbes starved, the structure completely collapses.
Oh, wow.
The high-rise apartment building is reduced to individual, disconnected grains of dust. When the wind blows, that dust scatters into the atmosphere. When it rains, because there are no pores to absorb the water rushes over the surface, taking the loose dirt with it in chaotic mudslides. The energy and structure have entirely dissipated into disorder. That is high entropy.
That physical explanation makes it so clear. An unhealthy soil is quite literally a physical system falling apart into chaos. And the text backs that up by stating another benchmark of health is that there is no damage to or loss of the fundamental components.
Yeah.
It specifies that erosion should only happen at geological rates.
Geological rates refer to the natural, incredibly slow process of wind and water wearing down landscapes over millennia.
Yeah.
Think of how the Grand Canyon was formed over millions of years.
Right.
Unhealthy soil, due to its high entropy and lack of biological structure, experiences accelerated erosion. Entire topsoil layers wash away in a matter of decades. Finally, a healthy soil has no accumulation of contaminants. So an unhealthy soil is simply the converse of these vital signs. Low biological diversity, poor absorbency, high nutrient leakage, high entropy, accelerated erosion, and toxic buildup.
It sounds so straightforward when we lay out the diagnostic criteria conceptually. A doctor has a checklist, they run the tests, they diagnose the patient.
Yeah.
But here's where the plot of our source material really thickens and where the science gets contentious.
Oh yeah, very contentious.
Because defining soil health conceptual on a Wikipedia page is one thing. Actually proving it, measuring it, and agreeing on those measurements in a laboratory is causing a massive turf war in the agricultural community. The diagnostic tools themselves are the subject of intense debate.
They are. And to understand why the scientific community is fracturing over this, we have to look at the history of soil testing. For the vast majority of the 20th century, especially during the post-WWII agricultural boom, soil testing was predominantly focused on chemistry.
Because that was the era of the soil quality mindset, the era of the blank slate.
Exactly. You scooped up some dirt, sent it to an agricultural lab, and they ran chemical extractions to tell you exactly how much nitrogen, phosphorus, potassium, and calcium were present. It was an elemental inventory.
Right.
Based on that inventory, they would tell you exactly what synthetic chemical fertilizer you needed to buy to grow your crop.
But as the paradigm shifted toward soil health in the 1990s and 2000s, those chemical tests suddenly weren't enough. If we now know that soil is a living system requiring a composite well-being of biological, chemical, and physical properties, taking a purely chemical inventory is like trying to diagnose a patient's liver disease by only looking at an X-ray of their arm.
That's a good way to look at it.
You are missing the vital organs entirely.
The testing had to evolve to capture the whole picture. The text notes that pioneers in this field began creating new, comprehensive testing packages. Woods End Laboratories, which is a private research lab in Maine, offered a multidisciplinary soil quality package as early as 1985.
Wow, 1985.
Yeah. Later, Cornell University, a major land-grant college in New York, introduced a comprehensive soil health test in 2006 that became highly influential.
What are these pioneering labs doing mechanically that the old chemistry labs weren't?
They began testing all three pillars. They test the physical aspects, performing what is known as aggregate stability testing.
How do you test that?
In a lab setting, they take a dried chunk of soil and aggregate, put it on a sieve, and simulate heavy rainfall by dropping water on it. If the biological glues and fungal nets are intact, if it has low entropy, the soil chunk will hold together under the water pressure.
And if it's degraded?
If it is degraded, it will instantly melt through the sieve into mud. That physically measures the structure. They still test the chemical-mineral balance, of course. But crucially, they added biological analyses. Today, these biological tests are considered the absolute hallmarks of modern soil health testing.
And the text gives a highly specific example of this biological testing, which frankly sounds like something out of a science fiction movie. The CO2 burst test, also known as soil respiration. I understand testing chemistry, but how on earth does a lab technician test the breath of dirt?
The mechanism of the CO2 burst test is actually beautifully elegant in its simplicity. Remember our massive African elephant of invisible microbes?
Yes, our 7-ton elephant.
Like all living organisms, those bacteria and fungi must breathe. They consume carbon-based organic matter in the soil, they metabolize it, and they exhale carbon dioxide as a byproduct.
Wait, so they are constantly exhaling underground?
Yes. In the lab, technicians take a dried soil sample, which forces the microbes into a dormant, sleep-like state. Then they place the soil in a sealed jar and re-wet it.
Okay.
The sudden influx of water acts like an alarm clock. The massive population of microbes wakes up all at once and immediately begins frantically consuming organic matter and metabolizing. The lab captures and measures the burst of carbon dioxide they collectively exhale over the next 24 hours.
You are literally measuring the lung capacity of the soil biota.
The new metric is direct and undeniable. A massive burst of CO2 means you have a large, active, biologically diverse population of microbes that are ready to cycle nutrients. A tiny, weak puff of CO2 means your microbial city is a ghost town. The soil is biologically dead. Other commercial labs have been heavily adapting this specific procedure since 2006, trying to integrate this biological factor into routine agricultural testing.
Okay, this is where I have to step in and push back on behalf of our skeptical listeners. Because if this biological testing is so brilliant, if it finally gives us the holistic picture of our living soil metropolis and measures the actual life in the ground, why wouldn't every single university, agricultural department, and commercial lab instantly adopt it? Why is there a turf war?
This raises an important question, and the resistance is significant. If we look impartially at the very real, practical concerns of the established agricultural community, their hesitation makes complete economic sense. The institutional resistance to these new biological tests isn't born out of stubbornness or an anti-science bias. It comes down to predictability and economic risk.
Risk for the farmers.
Exactly. The established metric of soil fertility, those old chemical tests, are backed by decades and decades of exhaustive, highly funded crop response studies.
Explain the mechanics of a crop response model for someone not in the agricultural industry. What does that actually look like for a farmer trying to make a living?
Over the past 50 years, scientists have run thousands of field trials to build massive mathematical models that correlate specific chemical concentrations in the soil directly to crop yields. A farmer's profit margin is incredibly thin. They cannot afford to guess.
Right.
Under the traditional system, a farmer sends in a soil sample. The lab analyzes the chemistry and sees that the phosphorus is at level X. Because of 50 years of mathematical modeling, the lab can confidently tell the farmer, if you spend $10,000 to add Y amount of phosphorus fertilizer to your fields, the math dictates you will yield Z bushels of corn per acre, which will net you a $15,000 return. It is a highly calibrated predictive economic formula.
I see. The chemical test isn't just a biological assessment, it is an economic guarantee. The farmer is taking that crop response model to the bank to secure a loan for the season.
Precisely. The critics of the novel soil health tests, the biological tests, like the CO2 burst, they argue that no comparable mathematical models exist for biology yet. The science is too new. We know a big burst of CO2 means the soil is biologically vibrant and healthy, but we do not have 50 years of localized data to tell a farmer exactly how many extra bushels of corn that specific CO2 burst will translate into this harvest season.
The traditional agronomists are looking at the biological data and saying, this is fascinating ecological information, but a high CO2 burst doesn't give me a formula to calculate my return on investment. I can't pay my mortgage with biological potential.
Furthermore, critics argue that these biological indicators might be insensitive to day-to-day management changes. If a farmer takes a massive financial risk to adopt a new, expensive, sustainable practice like planting cover crops or buying specialized equipment to reduce tillage, they want a diagnostic test that will show immediate, measurable improvement to justify the expense to their bankers. Some studies, like one cited from the Soil Science Society of America Journal in 2017, argue that soil health indicators do not adequately differentiate among agronomic management systems in certain types of soils.
So we have a profound institutional gridlock. The biological pioneers and ecologists are saying, you are ignoring the actual life of the soil, which is the foundation of the whole system. And the traditional chemical labs are saying, your new biological tests don't give farmers the precise economic models they need to survive capitalism.
It's a really tough spot.
And according to the source material, both sides have totally valid, rational points based on their respective objectives. We aren't here to pick a winner, but it is clear why this debate is tearing the agricultural world down the middle.
It is a classic clash between long-term ecological preservation and short-term economic survival.
But while the scientific community has been debating mathematical crop response models in conference rooms, the actual ground beneath our feet has not been waiting. We have to look at the consequences of this gridlock. What has been the real-world cost of sticking only to the old models that prioritized maximum chemical yield and ignored the biology?
Us is huge.
The text reveals a statistic that is, frankly, devastating.
The physical cost to the environment has been catastrophic. The source text states that over the past 40 years, as these older, chemically focused soil testing methods persisted and drove intensive farming practices, USA soils have lost up to 75% of their carbon.
75%, that is 3/4 of the carbon, gone. And when the text says carbon, it specifically mentions a word that I want to define clearly: humus. What is humus physically for someone who isn't a master gardener?
Humus is the dark, incredibly rich, complex, organic matter in the soil that is created over long periods of time when plant and animal matter decays and is processed by microbes. It is the absolute lifeblood of the soil ecosystem.
Okay, so it's the rip stuff.
Physically, it acts as the ultimate sponge for water. Chemically, it holds onto nutrients with a magnetic-like grip so they don't wash away. Biologically, it is the primary long-term food source and habitat for our invisible microbial elephant.
So how does a nation lose 75% of it? Does it wash away?
A portion washes away through erosion, which we discussed earlier regarding high entropy, but the vast majority of it literally evaporates into thin air.
Wait, evaporates?
The mechanism is oxidation. When a farmer excessively tills or plows a field, they slice the soil open and expose the buried humus to massive amounts of atmospheric oxygen. The bacteria in the soil go into an oxygen-fueled feeding frenzy. They rapidly consume the humus, metabolize the carbon, and exhale it as carbon dioxide into the atmosphere. The carbon is transferred from the ground into the sky.
By prioritizing intensive mechanical tillage and ignoring the biological consequences, we essentially starved the microbes, destroyed the sponge, and stripped the architectural structure out of the soil. We turned low-entropy soil into high-entropy dust.
It caused a severe systemic decline in biological fertility and overall ecosystem functioning. Now, to maintain scientific rigor, the text does note that exactly how much the biological fertility has declined is still a subject of intense debate among soil scientists. However, the physical reality of the massive carbon loss is undeniable.
Yeah.
Many critics of the conventional agricultural system look at this massive loss of humus and argue that it is sufficient evidence that the old soil testing models have utterly failed us on a systemic level. They argue that by stressing maximum yield and chemical yield calibration to the exclusion of all ecological factors, vital biological systems were broken.
And when you break the biology, the chemistry stops working the way it is supposed to, which brings us to the cascading failures mentioned in the text.
If we connect this to the bigger picture, the cascading failures are deeply alarming because they extend far beyond the borders of the farm. Because we lost the humus, the physical and chemical sponge that holds onto things, the soil lost its structural ability to retain those synthetic chemical fertilizers we were pumping into it.
Walk me through the mechanics of that failure. A farmer applies nitrogen fertilizer to a field, expecting the crop to absorb it. What actually happens?
Because the soil is biologically dead, has high entropy, and lacks the magnetic grip of humus, the nitrogen doesn't stay in the root zone. When it rains, the water doesn't gently absorb into the aggregates. It rushes through the loose dust or flows rapidly over the surface. The water dissolves the synthetic nitrates and phosphates and carries them entirely out of the agricultural system.
They leach directly into the groundwater aquifers, or they run off into the streams and rivers.
Exactly. The text details how surface and groundwater pollution with excess agricultural nutrients has grown enormously. Because the old predictive models didn't account for the soil's biological capacity to hold the nutrients, farmers were applying precise amounts of chemicals for the plant, but the soil couldn't retain it. The massive runoff creates toxic algae blooms in rivers and ocean bays, effectively suffocating aquatic life and creating dead zones.
And this isn't just some historical footnote from the era before environmental regulations. The text drops a massive reality check. It says that by the early 2000s, this nitrate and phosphate pollution in the United States was reported to be the worst it had been since the 1970s.
Which is a staggering indictment of the methodology.
Right, because the 1970s was the era before the advent of modern environmental consciousness. It was before the Clean Water Act really took hold and reshaped industry. We technically had infinitely better technology, stricter regulations, and more environmental awareness in the early 2000s, but because we were fundamentally misunderstanding the soil as an inert chemical sponge rather than a living biological system, the pollution actually got worse. We were treating a symptom with precise chemistry while entirely ignoring the biological disease.
It perfectly illustrates the danger of systemic ignorance.
So we have lost massive amounts of carbon, we have starved the microbial workforce, and we have severely polluted the global water table because we were using diagnostic tools that only saw 1/3 of the picture. Acknowledging that we are in a deep, deep hole is the first step. But how do scientists propose we find our way out? If the measurement wars are gridlocked, how do we move forward? The text mentions a relatively recent concept from 2020 that seems to offer a practical roadmap out of the chaos.
The source introduces a vital conceptual framework designed to solve this exact measurement crisis. It was published by a researcher named Maharyan and his team in 2020. They recognized that the biggest scientific hurdle to improving soil health was the lack of a universal baseline.
It goes back to the medical analogy. If a doctor doesn't know what a healthy human heart rate is supposed to be, they have no idea if their patient is suffering from tachycardia. Without a baseline of health, you can't measure disease.
The problem with soil, as we discussed with the ecologist versus the farmer, is that perfect health looks different in every single geographic region. You cannot compare the baseline health of a desert soil in Arizona to a glacial till soil in New York. So Maharjan and his team introduced the concept of the soil health gap. The core methodology is to use native land in a specific localized region to establish the ultimate benchmark for that exact area.
Define native land in the context of this methodology.
Native land refers to a patch of the ecosystem in a specific region that has remained entirely undisturbed by modern intensive agriculture. It could be a surviving piece of native prairie grass, a virgin forest patch, or a protected nature reserve. That untouched soil represents the peak evolutionary potential for that specific climate, geology, and geography. It possesses its full, undisturbed microbial elephant, its maximum potential carbon storage, and its lowest possible state of entropy.
So the scientific method is actually quite straightforward. You go to the native prairie reserve, you extract a sample, and you run all the comprehensive new tests, the aggregate stability for physical structure, the chemical mineral balance, and the CO2 burst for biological respiration. You compile those metrics, and you get a numerical score. That score becomes your localized baseline of perfect, untouched health.
Yes, that native score acts as the control variable. Then you go to the managed agricultural land right next door or down the road, which exists in the exact same climate and geology. You run the exact same battery of tests on the farm soil. The quantitative numerical difference between the peak score of the native land and the degraded score of the farmed land is the soil health gap.
It is brilliant because it completely bypasses the theoretical arguments. It doesn't matter if the agronomist and the ecologist are arguing over abstract definitions. The gap gives them localized, indisputable data.
It provides a localized target. By establishing this gap, scientists and farmers can finally understand the exact quantitative difference in soil health status. But more importantly than just measuring the damage, it allows them to accurately and scientifically compare the efficacies of different agricultural management practices.
If a farmer decides to take a financial risk and starts planting cover crops to protect the soil over the winter, or buys new equipment to reduce their mechanical tilling, they don't have to guess if it is working. They can measure their soil year over year to see if the biological respiration is increasing and if they're actively closing the soil health gap and getting closer to their local native baseline. It gives them a compass to measure the healing process.
It transitions the science from merely diagnosing a decline to actively managing a biological recovery.
And to you, the listener, I want to take a moment to pause the heavy scientific explanations and tie all of this directly back to why this deeply matters to your everyday life. Because it is so incredibly easy to hear us talk about crop response models and oxidized carbon humus and biological respiration and think this is just academic squabbling happening in university laboratories. But this is not abstract.
Not at all.
If you are listening to this and wondering why you should care about a CO2 burst test in a lab in Maine, think about the price of food at your grocery store. That price is directly dictated by these crop response models and the fertility of the ground. When we talk about global food security, we're literally talking about whether that underground metropolis of microbes is healthy enough to digest the earth and feed the plants that feed the billions of people on this planet. When we talk about climate change, we are talking about the physical fact that healthy soil is one of the largest carbon sinks on Earth. Storing carbon in the structure of the soil is pulling greenhouse gases directly out of the atmosphere. When we lose 75% of that carbon to the sky because of aggressive tilling, we aren't just losing farm fertility, we are actively accelerating global warming. And when we talk about the purity of the drinking water coming out of your tap, we are talking about whether the dirt outside your city is a high-entropy dust bowl that leaches toxic nitrates into the aquifer, or a low-entropy, healthy biological sponge that filters and cleans the water before it reaches you.
This discipline touches every single aspect of terrestrial life. The paradigm shift from evaluating soil quality to nurturing soil health is a profound recognition that human health and soil health are inextricably linked. We cannot thrive as a species on a planet with a sick, degraded foundation. The biology will simply not support us.
It has been a wild journey unpacking all of this today. We started by completely redefining the ground beneath us, stripping away the old utilitarian idea of dirt as a passive resource to be mined, and rebuilding it in our minds as a holistic, self-sustaining organism. We visualize the sheer mind-bending scale of the microscopic metropolis, tons of fungal and bacterial elephants working tirelessly beneath the grass to cycle nutrients and act as the Earth's digestive system.
We explored the complex diagnostic framework required to measure this living system, acknowledging the very real, often difficult tensions between ecological preservation and the harsh realities of mass agricultural production.
We waded deep into the ongoing turf wars in the testing laboratories, looking impartially at the struggle to balance the need to measure biological respiration with the economic demands of predictive crop models that farmers rely on to survive. We confronted the devastating historical costs of our past ignorance, massive carbon oxidation, and severe groundwater pollution. And finally, we look forward to the hopeful, scientifically rigorous framework of the soil health gap, which finally gives us a localized compass to guide our ecological recovery.
It is ultimately a story of scientific awakening. As a species, we are finally learning to measure and respect the unseen infrastructure that keeps us alive.
We really are. But as we wrap up this deep dive, I want to leave you, the listener, with a final provocative thought to mull over. Something that builds on everything we have learned today from the source material, but pushes the logic one step further into the future. If we fully accept the hard science that soil is a dynamic living organism, a composite entity that breathes, digests, and can be diagnosed as clinically healthy or diseased, does it possess a lifespan? We discussed the terrifying statistic that U.S. soils lost up to 75% of their carbon due to historical mismanagement. If human agriculture continues to prioritize short-term chemical yields over biological health, and we deplete that carbon loss to 100%, does the soil effectively die? And if a patch of earth is clinically dead, biologically sterile, and completely devoid of its microscopic elephant, can it ever be resurrected? Or is it gone forever, reduced to nothing but sterile rock dust?
It's a terrifying thought.
How does viewing the very ground you stand on as a mortal entity, something that can live, breathe, get sick, and potentially die, change how you approach real estate, how we approach generational farming, and how we view the long-term footprint of human habitation on this planet?
It is a profound existential question that challenges our entire relationship with the Earth, and one that the next generation of soil scientists will undoubtedly have to answer.
They absolutely will. Next time you look out your window or walk across a park, I guarantee you will not just see inert dirt. Thank you for joining us on this deep dive into the hidden world beneath our feet. Keep questioning, keep learning, and we'll catch you next time.